I want to find the antiderivative of e to the x sine x. I don't see an obvious way to use a u substitution here, but I do see a product of functions, so that makes me think of the reverse of the product rule, which is integration by parts. And so I'm either going to use u's and v's or f's and g's to think about this. For me, I'm going to think of this as f's and g's, so I'm going to choose an f and a g prime, or equivalently I could choose a u and a dv, and then from that I'll calculate f prime and g, or du and v, and then integration by parts will tell me how I can simplify this. But the thing is here, if I take derivatives of e to the x, I just keep getting e to the x. Same with antiderivatives. And if I take derivatives of sine, I'm getting cosine, then negative sine, then negative cosine. So those aren't getting more simple either. But there's a looping property here where I can, if I apply this enough times, I will loop back to the original integral, and that will allow me to solve this problem. So I'll show you what I mean. I'll just choose f equals sine and g prime equals e to the x. My derivatives are easy to calculate. My antiderivative is even easier to calculate. So now integration by parts tells me I have f times g minus the integral of f prime g so I've traded this top integral for another integral that looks just as hard as the original one. You may think that I'm not getting anywhere, but I am. I'm just going to use one more step and then I'll be able to solve this, because if I do the same process here, then this integral will pop out. So let's do this again. I'm going to choose a new f and a new g prime. So I'll do f equals cosine, g prime equals e to the x. Calculate f prime and g. And update this. E to the x sine x doesn't change. But this, I now know, so I'm going to put all this in parentheses. This is equal to f times g minus the integral of f prime g. F prime g is negative e to the x sine x. And now, what I mentioned would happen is that this integral will show up again. That's really useful because now when I simplify the right-hand side of the equation, I'm going to be able to move this over to the other side and combine it with this one and then solve. So when you distribute this negative, these two negatives are already canceling each other out. So I have a minus this term and a minus this term. I'm going to add this term to both sides of my equation. So in my equation, this is the left-hand side, and this is the right-hand side. When I add this to both sides of the equation, then on the left-hand side, I'm getting two of these. I have the integral of e to the x sine x plus the integral of e to the x sine x. That means I have two copies of that. On the right side, what I'm left with is e to the x sine x minus e to the x cosine x, and then this is gone. There's a plus c in here. I'm going to go ahead and add that here. I know that it will be there because I'm taking an antiderivative. I'm almost to the final answer. all I have to do now is solve for what I wanted algebraically, which means just divide both sides by 2. So if I divide both sides by 2, then this goes away. I get a 1/2 times all of this stuff. And there's no point in multiplying the 1/2 times a constant, because it's still just an arbitrary constant. So this is my final answer. If I take the derivative of this, I'll get a product rule here and a product rule here. Some stuff will cancel out. What I'll end up with, miraculously, is this thing. That would be good for you to check at least once. Make sure you come back to this. This way of using integration by parts to solve a problem is sometimes called the loop method, because you have to apply it more than once and loop back around to the original integral somehow, and then just solve algebraically for the integral that you were trying to find in the beginning.